Hi, welcome back to NMI. In this video we're going to talk about ANSI terminals and how you can leverage the escape codes designed for handling ANSI terminals in order to improve the output and the quality of the communication of your console applications and also other embedded systems like Arduinos and such. So let's take a look at it. In the early days of computing history, this is what a computer looked like. So we're talking here about 60s, 70s. This is an IBM 360. So computers, they didn't really have small screens or even LCD screens and keyboards. They were very big machines that occupied rooms, sometimes buildings, right? So on these computers, in order for you to interact or anyone to interact with them, it was necessary to use terminals. So here we can see what a terminal looked like. If we look here, in the very, very early days of computing history, a terminal did not even have a screen, right? So there was no CRT here. So a terminal was basically a typewriter, but not really. So this is why it's called a teletype, because you would type on the keyboard, but the information that you type does not go into the printer. It goes into the computer, into the host, and the host, so that is the input to the host, and then the host is going to do whatever the processing it is expected to do, and the output of that host, or the output stream of that host, lands on the printer and then it's printed out. So this is maybe a concept that might be familiar to anyone that studied C language or Linux. And if we look here, this is what we are talking about: a keyboard that acts as the standard input, right, into a process that, in the case of computer terminals, it's usually a remote process that is running outside the terminal on a host machine. The host machine is gonna provide an output through the standard output to the display on this terminal, right? And also provide a secondary stream that is the standard error. So you can represent errors or data out on the display, or in the case of teletypes, on the printer, right? So this is a very familiar construction. Again, that is what we see on C language, basically because that was the reality in the 70s when the C language was designed and terminals were the way you would communicate with the computer. Just a quick remark: this kind of terminal, the teletype, is the reason why we still see, even these days, the TTY devices on a Linux or Unix machine, right? TTY stands for teletype, so it's the abbreviation of teletype in terms of Unix environment. Moving forward, I think in the 70s, or around, probably mid or early 70s, terminals with CRTs were starting to become or to be more common, right? So this is the VT100. a very, very famous terminal. So here we can see still a keyboard for the input and a screen now as the output. So you don't have a printer as the output, right? Now, why are we discussing terminals? Well, because this guy in particular, the VT100, was one of the first, or maybe it was the very first one to implement what we call ANSI scapegoats. So that terminal could not only receive input from the keyboard and send it to the host, but also get special commands from the host that would format how the representation of the data is displayed on the screen, right? So this, there were other methods of doing that, but ANSI was one standard that was designed in order to allow more compatibility between all the terminals that were selling at that point. Now, talking about the VT100 that was manufactured by Digital. This was, as I mentioned before, was one of the first terminals that implemented the ANSI scape codes. So it allowed, those scape codes allowed a terminal that does not have a lot of local processing. Basically, doesn't have any local processing, even though it has a CPU. But the ANSI scape codes, they allow this terminal to send special data to the host. For example, cursor keys that we see here and other special keys, and to receive special codes from the host that allow the host to control where the data is going to be displayed on the screen, and to also control like font size, the font style, and colors when there's color available, and things like that. So ANSI codes were designed to allow this level of control from the host, because terminals were getting fancier, and there was the expectation to see like better data output in terms of presentation on a terminal. So that leads us to the ANSI scapegoat, which we can see here on the Wikipedia page. So as I mentioned before, these codes, and the reason we say scapegoats is that they are preceded by the scape character on this standard. The scapegoats allow the host to send or to receive special commands from the terminal. And the beauty about ANSI codes is that they're still supported even nowadays. So basically, all Linux consoles and most of the terminal emulators, and if you stop to think about that, a terminal emulator, like a serial terminal application like Minicom and many others, they are effectively emulating some of these ancient terminals that we just described, like the VT100, for example, or the VT52, right? So as long as the terminal emulator or terminal application that you're using is compatible with ANSI scapegoats, which usually most of them are, we can use those scapegoats to control how we display data on the console application, or on the data terminal, on the terminal emulator. And this is what we're gonna see in this video. I'm gonna show you a library that I wrote for Arduino, but the beauty of this library is that I wrote it in a way that it's totally portable, and I'm going to show you the same library running on Linux console, where we're going to play a little bit of Pong, and I'm going to take that application and show you that we can run it with some modifications, because the environment is slightly different, but with some modifications on the application itself, we can have it running, for example, on an Arduino. So Linux console, in my case, a 64-bit machine, and the Arduino that I'm using, an AVR-based microcontroller, 8 bits, both of them performing in the same way and running the application in the same way. So from the user's perspective, which is us in this case, you're going to see on the video, you can barely tell if the host that is running that application is really the Linux machine or Arduino. So let's take a look at how that really works. So here we have the library that I wrote. It is composed of a header file and a source file. On the header, there is basically, we are declaring some type defs. So I decided to create a type def for some standard colors that you can see here, and another type def for the output of the input processing function that we have on the fancy terminal. By the way, yeah, I named the library fancy terminal, and the reason for that is that, you know, it's just fancier output. Usually you have very ugly text-based output on console applications, especially on embedded systems. That's the usual way. But with the fancy terminal library, you can have a more or a nicer output on your application. And we're gonna see that by using this library, you can really sometimes replace the need or avoid the need of having an application that process the or performs the communication with your target, right? Because in the past, sometimes I had to do like design GUI, a graphical user interface running on a PC that would interface to my target device, and just present data on the screen. But with a solution like that, this one that we are gonna see here, you can sometimes avoid having to write such an application, and also, because you don't have to write an application, that means that on almost any machine, you're going to be able to connect to your system through a console interface, a terminal emulator, which is available or on basically any computer, and use that to have an output that is going to look the same on any machine. So that, I think, it's a very nice thing to have. So okay, so we have some special output codes for the input that you can get from the input processing function. Key none when there is no key pressed, key standard when there is one of the standard keys like character, numbers, whatever, and then the special keys like key up, key down, left, right, and keypad 5, and so on, right? There is another struct that packs the special terminal key output here and the standard key, in case you get key standard as the output here. Here we have all the prototypes of the functions that we support. That reminds me that I should probably add a more descriptive header on each one. I'm gonna do that later. Because this library targets multiple platforms, we have these if defs here, and that is basically on Linux. The terminal output is gonna use printfs, and terminal flush is gonna use fflush. But on Arduino, we have to use serial, the C++ library that is provided by Arduino. So we use serial.print and serial.flush for the same application. Now, I am not going to describe all the library here. I think that is pointless. I'm just going to show you how the basics work, or the basics, yeah, how the basics work. So the most important functions in my mind here are these ones: set cursor xy and print char xy. Let's start with set cursor xy, which is most probably the most important function in this library. So if we are targeting Linux, there is only one output. The output is going to be \x1b. So this how you insert the escape character, followed by opening square brackets, %age, which is a hex, %age u, which is a hex number, followed by a semicolon and another %x age, %age u, followed by age. So this is the escape sequence, the ANSI escape sequence for setting the terminal cursor position, y and x coordinates, right? We can see here that the way Arduino works, because serial.print cannot have this kind of formatting codes on a single line. On Arduino, I had to break that string in pieces. So we have the first part, escape, and opening square brackets, then the y coordinate, then the semicolon, then the x coordinate, and then the age that goes in the end. So when the terminal emulator receives this sequence, it's gonna move the cursor to the coordinate that you specified. What else we have here? We have functions to set the foreground color, one of those colors that we defined with that enum. We can also define the background color, BG. We can make the bell ring on the terminal, but I'm not too sure that this is working. The last time I tried it, it was not fully working. I need to understand why. Also, these two are important: set cursor visible and set cursor invisible, because as we are gonna see, the code is using all these functions to move the cursor around and draw things or print characters in those spaces. If you leave the cursor visible, you're gonna see the cursor moving like crazy, right? That is not very nice user experience. So you can set the cursor to be invisible with this escape sequence, and then the cursor is going to disappear, so you're not going to see the cursor moving around, which is a nice thing. What else? This is the escape code for clearing the screen. resetting the terminal color so that they move or they are reset to the default colors. This is just an extension of set cursor XY, so this function is going to not only move the cursor but print the character that you provide. And then we have functions for drawing horizontal lines, vertical lines, rectangles, and filled rectangles. And finally, we have the input processing functions. So we have the initialization terminal and the dinit function that you call after you're done with the terminal. Read terminal input is where the magic happens for processing terminal input. So here we see the use of the struct that we defined here, right? This struct here, it has these two fields. So on Linux, we're gonna use read to read the standard input. So we try to read 4 characters and return them on this string here. And this variable is gonna tell us how many bytes we were able to read. And oh yeah, well, it's another important thing. On Linux, because read is usually gonna block until it receives the number of characters, we are performing or setting the terminal here to be non-blocking, and this is where the magic happens. So here we are forcing the terminal to be non-blocking, so that when we perform this read operation here, it won't block. So it will return right away. If there is 1 byte in the input device, it's going to return bytes read 1. If there's nothing, it's going to return 0, right? When we are targeting, oh, there is a double semicolon here. When we are targeting other platforms like the Arduino, then we are using serial.readbytes. And if we see here on Arduino, because read is also gonna be, is it gonna be blocking? I think it will. I'm not too sure. But anyway, we set a timeout on the serial port. In this case, we're setting 50 milliseconds, so that when we run serial.readbytes here, we're gonna wait for 50 milliseconds. So if there is nothing, after 50 milliseconds we return and byte read will be 0. If we are successful, then string is going to receive the number or the string that we received from the terminal. Oh yeah, you don't need this because str is already a pointer. Okay, so once we return from this reading function, we are going to perform this processing here. So we check if the number of bytes that we received is 1 or more, and if it is, then we check if the byte is again the escape character, because the escape sequence is valid both ways, right? So we send ANSI escape characters to the host, and the host sends ANSI escape characters to us. So if we detect escape then and followed by an opening square bracket, then we enter this kind of exception processing. Oh, this is ugly. Let me use another tab here. And let's add a break here just in case. So if we receive opening square bracket followed by A, that is a key up. Followed by B, it's a key down, and so on. How do I know what are these sequences? If we look here at this page, we are gonna see that the colors are defined here, cursor controls here, so that function that we saw, the escape code for our for moving the cursor, you can see it here, line, column. And yeah, the same for colors, for setting the colors. There are other modes that I didn't even include, but we can easily extend. So you can set to the dim faint mode. Blinking, I think I tried, but it didn't work properly. Here you can see the colors, how you set the colors. Screen modes, make the cursor visible and invisible. So that's what we already mentioned. Function keys. And here, as I mentioned, we can see the cursor controls. So here you can move by give a specified number of lines, but if you do not provide, you just use A, it's going to be one line. So you can use A for up, cursor up, B for cursor down, C for cursor right, and D for cursor left. And if we look at our code, that's what we are doing here, right? What else? I added, oh, we need another tab here. I added this processing for function keys. I'm not too sure. I know that they're following the spec, but I'm not too sure if they are working properly. I tried and they didn't work, so I'm gonna have to investigate what is wrong here. Or if you know what is wrong, please let me know in the comments and I can fix or the library. And that's basically it. So I'm gonna save. Let me just check git status because we performed some changes to the library. Git add, let's make git add this. Before we do that, let's make sure that I didn't change or that I didn't do anything wrong. That happens a lot. So let's go into the examples. ls cd examples Linux Pong, and we have our make file there. So we just type make, and apparently it worked, no problem. So we run Pong, and what is happening here? Wait, this is not right. Okay, so this output is not expected, but I think I know what is causing it. I was testing before these. Yeah, I don't think. Let me check. If we remove this additional character here and we make Pong again, oh, there you go. Yeah, I was testing something before, and so yeah, now since we're already talking about Pong, so I decided to implement something to demonstrate how nice the output of a library like this can be, and I decided to implement a little game. And I think Pong is a very nice one because it's one of the first video games ever, right? So here is my implementation of Pong. I'm not gonna go through all of it, but the main function here is as usual, as it should be, pretty small. And we have an infinite loop here where we draw the paddles, process input, process the ball, and we check if the game is done or over. So here it is running on the terminal. There's this small animation here from the blink function here. So it draws the text in yellow and then erases it. So that gives this blinking feeling here, or appearance. You can see that we're processing cursor keys here, and W and S for the other player, right? So everything works as expected here. You can see different colors on the screen. Now, if we look on the text here, the process input, you're gonna see that if we got standard keys, Q, it's for ending the game, quitting. W and S for moving the paddle up and down. And space here starts the game, and that's what is stated here. So let's press start, or space, sorry. And here we go. Now the ball is playing, and you can see that the animation is pretty. Oh yeah. You know what happens? The ball was moving in diagonal, so my paddle was not well positioned. Yeah, on this game, every time the ball collides with the paddle, I decide a random direction for the ball, and it works pretty nicely. I'm proud of this little game. It runs smoothly on the terminal. Oh, I don't want to. Yeah, so that's it. So we press Q and we get the prompt back. So this is Pong on Linux console. Now, if we look here, there is another example inside the Arduino for a Pong implementation Arduino. It is basically the same game, but obviously, since we're running on Arduino, I need to move some stuff to the loop function, since Arduino does not process or does not run a main function. And also the initialization stuff I moved to setup. Obviously, you need to initialize the serial port because on Arduino there's no real console, so everything is going to happen through the serial port. But all other functions they work exactly the same. Here we have the Arduino IDE. Let's take a look. Let's build the code. So it's a little shy of 4K of the program space usage, which I think it's good. Now let's upload the code to the Arduino board. Uploading. Done uploading. Let's open a new terminal window. And let's use the screen command on the TTY device that we have the Arduino, and see, this is a fancy teletype. It's a USB teletype with the speed of 115/200 and let's see what happens. And here we go. This is Pong running on Arduino. It's exactly the same application as I mentioned, well, with small changes just to adapt to Arduino, but the library is exactly the same. And you can see here that, oops, the game works or plays in the very same way. I don't know about you, but I think that is pretty cool. So we exit screen by Control A, K. Really kill this window? Yes. And we are back to the Linux console. Now let's have a look at the HMI application. So one nice thing about the library is that I merged this library, or I sent it to the Arduino repository. So now it's part of the Arduino environment. So if you go to the examples here and we scroll down to Fancy Terminal, Arduino, and we have the examples here. So you can, so that means that you can, if you have Arduino IDE, you can do the same. Just search for the Fancy Terminal. Let me show you. You can go to Manage Libraries here and Fancy Terminal. And here we go, installed. Oh yeah, let's update to version 1.03. Updated. Now, once the library is installed, we can load the other application. Let's close this window. And now we can also build this code here. A little bit over 4K, 383 bytes of dynamic memory, which in this case is static RAM. Let's upload the code to the board. Done uploading. Now we run the same screen command again, and here we have our HMI. So we can see here that we have, well, we didn't talk about the code, so let's take a look at the code first. So the HMI code is, I'm not gonna walk you through the whole code, but it's basically split in a similar way to Pong. We have, if we look here, the main loop, we have three functions: process input, do hardware interface, and do screen update. So on the do hardware interface, we basically read the analog inputs and we update the LED state. The screen update, we print out the readings, the maximum, current, and minimum readings of the ADC channels. We also update the state of the digital pin connected to the switch on the board, and we update the state of the LED on screen according to the actual state of the LED. We have functions here to draw the screen. Another thing that I want to mention is about, so here where we are performing the ADC measurement, I want to highlight that we're not using floats, which it's very common that I see on Arduino. I don't think float is a good idea when you're working on a small microcontroller. What we're doing here is fractional arithmetic. So this is a little bit more complex to do in terms of like there's more work here in terms of programming, but it's less expensive in terms of code, the final code in terms, and this is a little bit more complex to code because it requires more operations, but they're all integer, so it's way less expensive than floating point operations, which on an 8-bit microcontroller they are gonna require, they're all software, right? So yeah, so that's it. The ADC sampling we only do every specified interval, and we can see here on the top that we do the screen update every 100 milliseconds and the ADC sampling every 50 milliseconds. So okay, that's it. Now let's try the code. We already uploaded it to the board, so, and it's running here. So here we can see the analog readings, the status of the switch, and the status of the LED. And if we reset the measurements here, we can see that there's no change. This is on the potentiometer on the board. So let's try to change the potentiometer. Changing the potentiometer, we can see that we are changing the values that we read there. We can go to one extreme and to the other. Now we set the minimum and maximum, minimum to 0, maximum to 5 volts. We can also check the switch here, and we can see, we can see the LED changing the state. Well, that's it for this video. I hope you liked this content, and if you did, please subscribe to my channel and feel free to add any comments, and see you next time. Bye.